Can you guys
Yes.
see? All right, correct. So let me know when I can start.
Okay. Are you ready?
Yes.
Okay. Let's begin. You have 15 minutes.
Right, cool. Good afternoon, everyone. My name is Krisnawan, and today I will be presenting my CS687 capstone project advised by Professor Kim. So my project is titled AI-Generated Image Detection Model. It asks a question that's becoming increasingly urgent. As AI-generated images get harder and harder to distinguish from real ones, how do we build detection systems that don't just give a yes or no answer, but actually show you the evidence? I'm sorry, Tao, would you mind muting yourself? Thank you. So here's a quick agenda of what we'll cover today. I will start with the problem statement and motivation and why this matters and what gaps exist in current research. Then I will walk through the background and related work to give you context on where the field stands. And from there, I'll get into my approach and design, followed by implementation on how the system is actually built. And next, we'll look at the data collection and analysis, which translate to our findings, conclusion, and future works. And we'll wrap up with a quick demo, and then I'm happy to take questions at the end. So let's start with the core problem. Current AI image detectors mostly operate as black boxes. They will tell you an image is fake, but they cannot tell you why. If you're a forensic investigator or someone making a high-stakes decision, a bare classification without any evidence to back it up isn't very useful. On top of that, these detectors are surprisingly fragile. Something as simple as compressing an image, resizing it, or adding a little noise, so the same kind of processing that happens every time you upload a photo to social media, can significantly degrade detection accuracy. So we have two compounding problems: detectors that cannot explain themselves and detectors that break under real-world conditions. And that's the gap this project is designed to address. Building on that problem, here's why it matters right now. AI is getting generally good at creating synthetic media that's indistinguishable to the human eye. It poses a real threat to digital integrity, journalism, and forensic investigations. Existing detectors have largely been built to maximize raw accuracy, but they ignore a critical need: explainability. A forensic investigator cannot bring a binary classification to a courtroom. They need to point to something specific, like a visual artifact or a pattern, and say, this is why this image is fake. That's the research gap this project targets. By combining a high-performance convolutional neural network with explainable AI techniques, specifically GradCam, the goal is to produce detections that are not just accurate, but forensically defensible. To understand why this is a hard problem, early forensic detectors were built around the mathematical fingerprints left by GANs, generative adversarial networks. But when diffusion models came along, they left completely different kinds of traces. The effectiveness of these older models became questionable. There's also a persistent overfitting problem where detectors tend to get very good at recognizing one specific generator's artifacts, but fail when they encounter a new architecture they have not seen before. Real-world image handling makes this even worse. Compression, resizing, social media re-encoding, all of this distort the high-frequency artifacts that detectors rely on. And finally, none of these symptoms produce an audible chain of evidence. For legal or forensic use, a binary output just isn't enough. These four limitations together set up exactly what my project is trying to solve. I reviewed three key prior studies that directly informed my approach. Barham and Nguyen in 2023 fine-tuned an efficient net B4 using transfer learning across 12 different synthesis models. They achieved strong cross-modality accuracy up to 99% on unseen generators, but their training was GAN only, making them vulnerable to diffusion-generated images and real-world degradations. That work directly inspired my use of EfficientNet, but I pushed EfficientNet B7 to include both GAN and diffusion data. Corvi et al. In 2023 trained individual detectors per generator, one for ProGAN and one for latent diffusion. They found that GAN-trained detectors perform poorly on diffusion images, which confirmed the generalization problem that I needed to address. Martin Rodriguez et al. In 2023 took a more forensic approach. They used pixel-level feature extraction techniques like photo response non-uniformity (PRNU) and error level analysis (ELA). They achieved up to 98% accuracy, but their dataset was small and they stopped short of full explainability, which is exactly where my GradCam integration picks up. Together, these three works define both the state-of-the-art and the remaining gaps. So here's how I approach solving those gaps. The primary goal was to build a forensic framework and not just a classifier, a system that can provide interpretable visual evidence alongside its decision. The model is designed to detect the specific artifacts that AI generators leave behind, things like repetitive noise patterns and checkerboard artifacts that appear in the upsampling layers of both GANs and diffusion models. To avoid the overfitting problem I described earlier, I fine-tune an efficient NetB7 backbone using transfer learning on a balanced dataset of 90,000 images, spanning both GAN and diffusion generate sources so the model is unlocked into one generator signature. And critically, I integrated GradCam, which generates visual heat maps highlighting the exact regions of an image that drove the classification decision. That's what moves this beyond a black box and towards something forensically usable. This slide shows the overall system architecture. The system flows through 4 stages, starting with data collection, where real and synthetic images are collected and generated. These images are loaded and labeled into the pre-processing layer, where images are cropped, normalized, and converted to tensors. Then they move through the efficient NetB7 classification backbone, which outputs a probability score. Finally, into the GradCam explainability layer, which generates the visual heatmap overlaid on the original image. The end result is that for any given image, the system produces 2 things, a classification, real or synthetic, and a visual map showing where in the image the evidence is. So I'll walk through how the system was set up. Starting with the data generation layer, I used 2 programmatic pipelines to generate synthetic training data, a stable diffusion pipeline to produce 7,500 text-to-image assets, and a style GAN pipeline for another 7,500 synthetic human face images. This gave me control over the synthetic portion of my dataset. In the preprocessing layer, images are organized into an image folder structure with real and synthetic labels. Training uses random crop to extract local patches, while validation uses center crop for consistency. Everything gets normalized into floating point tensors compatible with the pre-trained efficient NetB7. The core classification layer uses Google's efficient NetB7 with a single logit output, keeping it lean for a binary forensic detector. For model training, I used BCE with logits loss for numerical stability, an Adam W optimizer with gradient accumulation over 8 steps to achieve an effective batch size of 32, and a cosine annealing scheduler that runs over 5 epochs. The gradient accumulation was a practical workaround for memory constraints based on the available hardware. The data comes from 2 sources, external Kaggle repositories and my own programmatic generation pipelines. For real images, I use photography datasets from the same Kaggle repositories to represent authentic camera sensor patterns. This is important because those patterns are part of what distinguishes real photos from the synthetic ones. The final dataset is 90,000 images consisting of 45,000 authentic and 45,000 synthetic images. The synthetic side spans 4 generators, StyleGAN, Stable Diffusion, DALL-E, and Midjourney. This gives the model exposure to multiple architectures rather than just one. For the split, I use a standard 80-20 partition with 70,000 images for training and 18,000 held out for testing. Images are mapped into a binary label structure, 0 for authentic and 1 for synthetic. And all of the preprocessing follows the same pipeline I described on the previous slide, where random crop is used for training and center crop is used for validation. And tensor normalization align to ImageNet channels for compatibility with the pre-trained efficient NetB7. For training, I performed several data analysis steps to make sure the dataset was clean and that the model would be learning the right things. First, with spatial preprocessing. I ran automated validation to remove any corrupted files and enforce a strict 512 by 512 by 3 tensor shape across all images. This isolates high-frequency anomalies and prevents the model from picking up on resolution differences between real and synthetic images rather than actual artifacts. Second, the multi-source certification. By carefully balancing images across generators and real sources, I ensured the feature extraction layers would focus on structural, generator-specific artifacts rather than high-level semantic context, like this looks like a face or this just looks like a landscape. And the third, I checked for color channel invariance, calculating average, brightness, and saturation across real and synthetic classes to confirm there weren't any systemic color biases that could give the model an easy shortcut. As for the evaluation, I used a sigmoid activation to convert raw logits into probability scores with a 50% decision threshold for classification. Accuracy, precision, recall, and F1 are calculated using scikit-learn. And those 4 metrics are shown right here on the slide with 85.44% accuracy, 97.71 precision, 72.58 recall, and 83.29% F1. So the model achieved 85.44% overall accuracy on the 18,000 image test set, which establishes a strong baseline for this kind of forensic detection task. The most impressive number is the synthetic precision at 97.71%. meaning when the model says that an image is fake, it's right almost 98% of the time. For a forensic use case, this is where the false accusation could have serious consequences, and that's exactly what this kind of variability we want. However, synthetic recall came in at 72.58%, meaning the model missed about 27% of synthetic images. So this tells us that the model is highly conservative, it almost never flags a real image as fake, but that caution comes at the cost of missing some synthetic images it has not seen patterns before. F1 score of 83.29% backs up the strong precision and recall trade-off. This was further confirmed by a batch evaluation of 40 images from newer generators, such as Midjourney, ChatGPT, and Gemini, where we saw a 65% false negative rate. These are generators that were not well represented in the training data. On the positive side, the GradCam.
Excuse me. Just a reminder, you have 5 more minutes.
Thank you.
Thank you.
So on the positive side, the GradCam hit maps worked as intended, successfully localizing upsampling grid artifacts and GAN checkerboard patterns, giving us that human interpretable visual evidence we set out to produce. So to bring everything together, on the result side, the fine-tuned efficient NetB7 pipeline successfully distinguishes authentic photography from synthetic media across both GAN and diffusion-based generators, achieving 85.44% overall accuracy. The high synthetic precision of 97.71% confirms the model is suitable for high-stakes forensic investigation, where minimizing false accusation is the priority. On the contribution side, the key advancement here is moving beyond black box binary labeling. By integrating GradCam, the framework produces visual localization maps that highlight the specific artifact regions driving each decision, making this not just a detector, but a forensically interpretable tool, which is the core research contribution. On the limitation side, to be transparent, the 72.58% synthetic recall and the 65% false negative rate on newer generators tell us that the model isn't ready for deployment as is. It needs broader training data, threshold optimization, and ensemble strategies before it could be used in real forensic workflow. For future work, there are a few directions for extending this research. On the dataset and robustness side, the most immediate need is expanding the training data to include outputs for newer commercial generators like Midjourney, ChatGPT, Gemini, etc. And ones that exposes the 65% false negative rate. I'd also want to include images that have gone through common post-processing degradation like compression and social media encoding to make the model more resilient to real-world conditions. Extending training beyond 5 epochs using cloud-based GPU clusters will remove the memory bottlenecks I had to work around with the gradient accumulation. For optimization, I tuned the binary decision threshold using precision recall curves to better balance false positives and false negatives depending on the deployment context. I'd also investigate ensemble approaches combining multiple models to improve robustness against unseen generator architecture. For explainability, the natural step is going beyond GradCam to pixel-level attribution methods and actually studying whether richer explainability outputs can meaningfully change how human investigators make decisions in forensic workflow. And so I have a quick demo on how I prepare the image, process it, train a model, and evaluate the model. So here you go. And here are my key references that govern this work. For the full citations, they're available on my paper if anyone wants to dig deeper into any one of this. And that brings me to the end of my presentation. Thank you for listening, and I'll try my best to answer your questions.
Generate their actions.
Hello, we'll have 5 minutes for Q&A. Does anyone has the question?
Parameters that I
Hi, Andrew. I had a question. Did you have any ideas on how you could make the model generalize better on synthetic images? Any ideas you came across for that?
So yeah, my biggest problem is actually generating data from newer state-of-the-art generators. Because I looked online, if I want to use commercial generators, while they are cheap per image, they actually bundle it up as in like I have to generate thousands of images at once, which will cost me like hundreds of dollars. So unfortunately, I did not get to that point. What I did was I ended up using like a free available tools that I can generate stable diffusion method for my synthetic models and also a style GAN, but my style GAN is actually only for human faces because how the variational autoencoder works is it's highly tuned to create a specific type of images. For example, human faces or animal faces or cars. So I just had to pick one because my other limitation is the hardware. It took a lot of time to create the diffusion model images. So I had to kind of stop at a good point where I can just say that, hey, this should be representative enough. But as for to get better generalization, yes, you do want more data points from more generators. So you could be able to figure out the patterns for these different generators. Sorry if does that answer your question?
Yeah, no, that's really interesting.